What's up, guys? So I'm back with another question on acids and bases, and this time it's another past examination question paper. So let's just jump right into it. As you can see there, they're saying sulfuric acid is a diprotic acid. So we know sulfuric acid is H2SO4, and di obviously means 2, and then protic means protons. So we've got 2 protons, right? That's what they're saying. Okay, the first question says define an acid in terms of Lowry-Bronsted theory. Right, so obviously we know that there are 2 theories, the Lowry-Bronsted theory and then the Arrhenius theory. And 2.1 acid is simply a proton donor. Sometimes some people would like to add in the presence of a base or something like that. And then according to Arrhenius, then you would know that an acid is a substance that ionizes in water to produce protons. However, in this case, they ask for the Brosted-Lowry definition. Okay, 2.12, they say give the reason why sulfuric acid is referred to as a diprotic acid. Okay, so obviously the reason is the fact that it actually have got 2 protons here, or it can donate 2 protons per molecule. So in other words, we're simply saying 2.1.2 it's a diprotic acid because it can donate 2 protons per molecule. And then they say hydrogen carbonate can act as both an acid and a base, underlined, and then it reacts with water according to the following balanced equation. So we can see hydrogen carbonate and then water to produce hydrogen carbonate and the hydroxide ion. They say write one word for the underlined phrase. So can act as both an acid and a base. That's a simple 2.1. A substance that actually can act as an acid and a base is called an ampholyte, or sometimes it's an amphoteric substance. Whichever is going to be easier for you to remember would do. An ampholyte, those are substances that when you add an acid to them, then they're going to react as bases, and when you add a base to them, they're going to react as acids. And many of the conjugate bases for polyprotic acids are going to act as ampholytes. For example, I can give you even the one for sulfuric acid, this HSO4 minus, and then H2PO4 minus, even HPO4 2 minus. All these can act as ampholytes, and even water itself is an ampholyte. These substances can actually react with either acids or bases. So those are examples of some examples of ampholytes, and you can see this substance acts as a base in the above reaction. Write down the formula of the conjugate acid of that substance. Right, so in conjugate acid base pairs, the first thing that you just have to identify is on the left side of the equation, which one is the acid and which one is the base, and on the right side of the equation also, which one is the acid and which one is the base. So the way that you actually do this is by identifying which of the 2 actually donated protons and which one accepted a proton or protons. So you can see if I look at this, it was HCO3 minus on the left, and then on the other side it became H2CO3, which means it actually accepted an additional proton. In other words, water donated a proton to this. And since we're saying an acid is a proton donor, then that simply means that water here becomes our acid, and then this will be our base here. So if a substance or if a compound, this side is a base, and then what it ends up being the other side will be definitely the conjugate acid. In other words, as you can see here, this is a base, and then this other side, it becomes the conjugate acid. So in other words, this will be an acid, and then of course for water, it was acting as an acid here, and the other side it will be a base. So you can see this is very clear also because the hydroxide ion here is also an indication of a base, or it is basic. So that is very clear. So according to our question, they're saying write down the formula of the conjugate acid. So this will be the conjugate acid. In other words, it's gonna be H2CO3. That's our conjugate acid. All right, let's move on to the next question. Right, in this question, they're saying Elena accidentally spills sulfuric acid of concentration 6 moles per dm cube from a flask on a lab bench. So let's say this is a lab bench, and then the person spills some sulfuric acid here, and this sulfuric acid is 6 moles per dm cube, right? And then her teacher tells her to neutralize the spilled acid by sprinkling sodium hydrogen carbonate powder on it. So they're going to sprinkle some sodium hydrogen carbonate, right? Okay, so and then they say, and then the reaction that takes place is assume that the sulfuric acid ionizes completely. Okay, so this statement simply means that H2SO4 is going to ionize to produce 2H plus SO4 2 minus. Okay, so that's what's going to happen there. And then okay, we've got the reaction between sulfuric acid, sodium hydrogen carbonate to produce sodium sulfate, water, and carbon dioxide is balanced. And then they say the fizzing due to the formation of the carbon dioxide stops after Elena has added 27 grams of sodium hydrogen carbonate to the spilled acid. So obviously what's going to happen here is that when you add the sodium hydrogen carbonate to the sulfuric acid here, H2SO4, what's going to happen is there is going to be a neutralization reaction. And that neutralization reaction, since it's producing carbon dioxide, that carbon dioxide is going to form some bubbles. Okay, so that means the amount of sodium hydrogen carbonate that was added was 27 grams. Okay, so now they're saying the first thing is they say calculate the volume of the sulfuric acid that was spilled. Assume that all the sodium hydrogen carbonate reacts with all the acid. Okay, so here this is very simple. The thing is we are going to solve this using the stoichiometric equation, where we know that hydrogen sulfate plus 2 sodium hydrogen carbonate will produce sodium sulfate plus 2H2O plus 2 carbon dioxide. Okay, so the way that we are going to solve this problem is we do have the concentration of sulfuric acid, right? And we know that we have an equation that says concentration is equal to number of moles over volume. So since we have the concentration, we can actually calculate the number of moles of the sulfuric acid, right? And then after calculating the number of moles of the sulfuric acid, we can use our concentration to calculate the volume. So this is where this 27 grams is going to help us. We are going to translate this 27 grams into number of moles of sulfuric acid that reacted with the 27 grams. So this is what we are going to do. We're going to first convert the 27 grams into number of moles so that we can be able to use the molar ratios, and then after that find the number of moles of sulfuric acid that reacted with 27 grams. So that's what we are going to do. So number of moles, in this case of sodium hydrogen carbonate, will be equal to the mass over the molar mass, will be equal to the mass is 27, then the molar mass of sodium hydrogen carbonate. But if you calculate it, it's going to give you 84 grams per mole, and then you're going to find your number of moles as 0.32 moles. Now, then you're going to use, this is a number of moles of sodium hydrogen carbonate, so you're going to, this is 0.32, and you want to find the number of moles of sulfuric acid that reacted with 0.2, so it's going to be X here, and you can see 1 mole of sulfuric acid reacts with 2 moles of that, so it's going to be 1:2, and then you do the cross multiplication. This one times that and this one times that is going to be actually 2x is equal to 1 times 0.32, and then x is going to be this divided by 2, which is going to give you 0.16 moles. This simply means that 0.2 moles of sodium hydrogen carbonate reacts with 0.6 moles of sulfuric acid. And then using this equation, our concentration is equal to number of moles over volume. Our concentration, remember, is 6 moles, so 6 is equal to 0.16 over our volume, so our volume is equal to 0.03 dm cubed. That's how you calculate the volume. Okay, great. Now let's move on to the next question. Okay, moving on to the last questions. As you can see, they say Elena now dilutes some of the 6 moles of sulfuric acid solution in the flask to 0.1 moles per dm cube. So take note here, very important, dilutes, right? That means they added some water to change the concentration from 6 to 0.1. All right, then they say calculate the volume of the 6 moles per dm cube sulfuric acid solution needed to prepare 1 dm cube of dilute acid. So this is very important here. You must understand how to prepare standard solutions. So to prepare standard solutions, you should know that we have a stock solution. And that stock solution usually is high concentration. In this case, this is 6 moles per dm cubed, right? And then that stock solution is going to be diluted, and it's going to be diluted in a volumetric flask. It's going to be diluted in a volumetric flask. Now, the container or the volumetric flask must be exactly the volume that you need at the end of the day. So in other words, in this case, our volume of the volumetric flask here is supposed to be 1 dm cubed. Okay, so now what we should take note of is that we are going to take a certain volume and then add it in the volumetric flask, right? And then after that, we are going to dilute with water up to the mark. So we are going to take a certain volume. We don't know this volume, and in other words, this is the actual volume that they are asking us about, right? So we have x dm cube that we need to add in here, and then we are going to fill it up to the mark, and the volume is going to be that certain amount. So you should take note that the volume that we add in here is going to be our volume 1, and then the volume that we end up with is going to be our volume 2 in dilutions, and then the concentration that we start with is our concentration 1, and then the concentration that we end up with of our standard solution is our concentration 2 right there. And this brings us to our dilution equation. And our dilution equation is like this. C1V1 is equal to C2V2, right? Where this will be our initial concentration, final concentration, initial volume, and final volume. Right, okay, so in this case, our initial concentration was 6. Our initial volume is the one that we want to find, and then our final concentration is 0.1 from our question, 0.1, and then our final volume is 1 dm cube. So if we rearrange this, our initial volume that we need to add into a 1 dm cube container for that standard solution to be 0.1 dm cube is going to be exactly 0.02 dm cube, 0.02 dm cube. Now they're saying during a titration, very important, we're talking about a titration of the 0.1 mole per dm cube sulfuric acid solution is added to an LMAir flask, is this one, the one that looks like this, or the conical flask. Is titrated with 0.1 moles per dm cube sodium hydroxide, right? They say the learner uses bromothermal blue, so this is an indicator, bromothermal blue. What is the purpose of the indicator, right? So this is very easy, 2.3.3. So you must understand that whenever you're doing or performing a titration, what you are going to do is you are going to use what is called a burette. In a titration, you're going to use a burette, and then you're going to use an Erlenmeyer flask or a conical flask. And then in here, that's where you're going to put your standard solution. And then in here, that's where you're going to put your unknown solution. In other words, the one that you don't know is concentration, right? With an unknown concentration. Here you know its exact concentration. In other words, the definition for a standard solution, an accurately prepared solution of known concentration. So now what you're going to be doing is you're going to be adding the standard solution into the unknown solution that you measured, maybe 10 centimeter cube or something. And then for you to know what is called the end point, where you're supposed to actually stop adding more of the standard solution, or where all the base or the acid have been neutralized by the acid or the base, depending on which kind of titration you are conducting, you need an indicator. Right? An indicator is the one that is going to show you that all the acid have been neutralized or all the base have been neutralized by the change of color. So whenever you're doing a titration, you need to actually know where to stop adding the standard solution to the unknown solution. You need to know where to stop the titration, and then that's the function of the indicator. So in other words, the indicator, so 2.3.3, the indicator is to show the end point, right? So the end point, like I was saying, is the position in a titration where all the acid have been totally neutralized. If you are titrating an acid with a base, or the point where the base is totally neutralized with an acid if you're titrating a base with an acid. So the function of the indicator is to show you that end point, to show you that point, because you can't actually see with your naked eye that, oh, now all my acid have been neutralized, so I must stop adding the base, or now my base is all neutralized, so I must stop adding the acid. So you need that visualization that will tell you that all the acid is now neutralized with the base that you're adding. Right, okay, so now let's move on to 2.34. Now they're saying, calculate the pH of the solution in the flask after the addition of 35 centimeter cube of sodium hydroxide. The end point of the titration is not yet reached at this point. So this is a very important question to understand. Remember, the question is saying, during a titration, 25 centimeter cube of 0.1 mole of sulfuric acid solution is added to an Erlenmeyer flask, right? So in other words, we're saying in this Erlenmeyer flask right there, they added 25 centimeter cube, right? 25 centimeter cube of H2SO4. So the concentration of the sulfuric acid, is equal to 0.1 moles per dm cube, right? We need to actually understand this question for us to be able to solve it. Okay, so then they're saying it is titrated with 0.1 mole sodium hydroxide. So in this case, our standard solution here was sodium hydroxide. And the concentration of sodium hydroxide was also 0.1 moles per dm cube. Okay, so they take the sodium hydroxide, they put it in there. Now they say, now we should calculate the pH of the solution in the flask after the addition of 35 centimeter cube of sodium hydroxide. So in other words, we are saying that, let's say here they just put exactly 30 centimeter cube. That means in here they added, and when they added, it's increased, right? They added 30 centimeter cube, 30 centimeter cube of the sodium hydroxide. Here is sodium hydroxide that was added in there. And then take note, they say that the end point was not yet reached. All right, the end point was not yet reached. And since the end point was not yet reached, that means number one, the solution here was still acidic. Why was it still acidic? Because there was more of the acid than the base. Because at the end point, we know that we reach at the end point when all the acid would have been neutralized with the base in this case. Now, let's continue. So, for us to find the pH, right? For us to calculate, or for us to be able to calculate the pH of a solution, we know that pH is equal to the negative logarithm of the concentration of the oxonium ions. So we need first to find this concentration of the protons or oxonium ions from all this information. So now what we are going to do is, first we're going to find out the number of moles of the sodium hydroxide that actually reacted with the number of moles of the sulfuric acid that was in 25 centimeter cubed. And then after we find those number of moles, we are going to find the number of moles that did not react. And that number of moles that did not react, we are going to use them to calculate the concentration of the number of moles of the protons or the oxonium ions, and then we use that to calculate our pH. So let's do that. We're going to calculate the number of moles of the sodium hydroxide. So let's calculate number of moles of the sodium hydroxide will be equal to the concentration times the volume, which will be equal to the concentration, as you can see, for sodium hydroxide is 0.1 times the volume times the volume is 30 centimeter cube. However, we have to convert it to dm cubed because our concentration is per dm cubed, so it's going to be 30 divided by 1000, and this is going to give us 3 times 10 to the power of -3 moles. And then now we also calculate the number of moles in the sulfuric acid. Number of moles in sulfuric acid will be equal to concentration times the volume, which is equal to concentration is 0.1 times the volume, 25 over 1000. This will give us 2.5 times 10 to the power of -3 moles. We should understand that here in this 30 centimeter cube that we added here, there were this number of moles, and in this there were this number of moles. And in that case, that simply means that we can actually now calculate the number of moles of what? Of the sulfuric acid that did not actually react by subtracting this 2.5 times 10 to the power of -3 minus 3 times 10 to the power of -3. And take note, we are subtracting because we know that these number of moles are the ones that will react with some number of moles from here. So from our previous calculation, we know that the number of moles of sodium hydroxide that we added is 3 times 10 to the power of -3 moles, and then number of moles of sulfuric acid is equal to 2.5 times 10 to the power of -32 moles. Right, so this is what we know, right? We know that in the amount of sodium hydroxide that we added to this Erlenmeyer flask, this number of moles are the number of moles that were present for sodium hydroxide, and this number of moles are the ones that were present for the sulfuric acid. So we know that from this equation here, H2SO4 plus sodium hydroxide, this will give us sodium sulfate plus H2O. So as you can see here, if we balance this equation, this is going to be 2, 2, and then it's going to be 2 here. So this is going to be 2 here. Right, so from this equation here, we can see that 1 mole of sulfuric acid actually reacts with 2 moles of sodium hydroxide. Hence, this simply means that if we have this number of moles of sodium hydroxide, which is 3 times 10 to the power of negative 3, we can actually determine how much of the sulfuric acid actually reacted with this by calculating this times that and that times that, and then 2x is going to be equal to 1 times 3 times 10 to the power of negative 3, and then our x, which is the number of moles of sulfuric acid that reacted. So this is number of moles of sulfuric acid that reacted will be equal to 1.5 times 10 to the power of negative 3 moles. So 1.5 times 10 to the power of negative 3 moles of sulfuric acid are the ones that actually reacted. So that simply means that from this, what was there before the reaction. So now after the reaction, because this number of moles reacted, we can subtract them from there. That simply means that number of moles that were left would be equal to 2.5 times 10 to the power of negative 3 minus 1.5 times 10 to the power of negative 3. This would give us 1 times 10 to the power of negative 3 moles as the leftovers of the number of moles of H2SO4 right there. So now, since we have our number of moles of sulfuric acid, then now we can actually calculate the concentration, right? The concentration of the sulfuric acid, or the concentration. Now, since we have the number of moles of the sulfuric acid, we can actually now calculate the concentration of the oxonium ions that will be left in here. In other words, the one that did not react. So we're going to use our equation. Concentration is the number of moles over volume. It implies concentration will be equal to 1 times 10 to the power of negative 3 all over the volume. Now, I need you to pay attention to this one. Remember, when we're adding in here, at first, there was actually in here, there was 25 centimeter cube of H2SO4. And then we added sodium hydroxide. We added 30 centimeter cube. So the volume of these two, we're going to add them, and then they're going to give us 55 centimeter cube. And that simply means that our volume is now going to be that much. Hence, we are going to divide by 55 times 10 to the power of negative 3. Right, to convert the centimeter cube into dm cube. And then our concentration is going to be exactly 0.018 dm cube. Right, great. Now that we have our concentration, we can now substitute in our previous equation. Right, remember we said pH is equal to negative log of the concentration of H3O plus. Okay, now before we substitute this value here in that equation, we must take note of the fact that the concentration that we just calculated here is the concentration of the sulfuric acid molecules. And since it's the concentration of the sulfuric acid molecules, remember, sulfuric acid is a diprotic acid. And since it's a diprotic acid, it produces 2 protons per molecule. And hence, that means our concentration is going to be double here. In other words, it's going to be times 2. Hence, we are going to substitute a value that is times 2 here, because the concentration of the oxonium ions will be double for each molecule of sulfuric acid. So that is going to be equal to the negative logarithm of the concentration, which is 0.018 times 2. And then our final answer, if we punch in our calculators, is going to be 1.44 is our final answer. Okay guys, this is the end of this question. If you like the way that I explained, please subscribe, comment and like, and I'll keep on making videos like this ones.